Imagine standing beside a massive cargo ship as it prepares to leave the harbor from the outside. It looks almost indestructible. Hundreds of meters long, carrying thousands of tons of cargo, powered by engines capable of producing enormous amounts of energy. Its steel hull appears thick enough to survive almost anything the ocean can throw at it, but there is one part of that ship that looks almost ordinary, a simple red layer covering the underwater section of the hull. It does not look powerful, it does not move, it does not generate electricity, and it certainly does not make the ship faster. Yet without that strange-looking coating, modern ships could lose speed, burn more fuel, suffer serious damage, and become far more expensive to operate. That red layer is anti-fouling paint, and its story begins with one of the oldest problems in maritime history: the ocean is alive. The moment a ship enters the water, the underwater surface becomes an opportunity for thousands of organisms looking for somewhere to live. First come microscopic organisms, then algae, then tiny marine animals, then barnacles, mussels and other creatures begin attaching themselves to the hull. At first, this might sound harmless. After all, what could a few tiny organisms possibly do to a ship weighing thousands of tons? The answer is surprisingly dramatic. Imagine taking a perfectly smooth metal surface and slowly covering it with thousands of tiny bumps. The surface becomes rougher and rougher. Water no longer flows cleanly around the hull. Instead, turbulence increases, drag increases, and the ship needs more power just to maintain the same speed. This problem is known as biofouling, and for sailors hundreds or even thousands of years ago, it could become a nightmare. Long before modern paint existed, wooden ships were constantly fighting the ocean itself. A ship could leave port looking clean and fast. Months later, its underwater hull might be covered with seaweed, shells and colonies of marine life. The ship would become slower, its crew would consume more supplies, and long journeys could become much more difficult for ancient sailors. This was not simply an inconvenience, it could determine whether a ship completed its journey at all. There was another problem too. Some organisms did not merely attach themselves to the ship. They could attack the ship. Wood-boring marine organisms could damage wooden hulls, creating weaknesses that threatened the entire vessel. So sailors began searching for ways to protect their ships. Different civilizations experimented with materials such as wax, oils, pitch and other substances. The goal was always the same: keep the ocean away from the ship's hull, or at least stop marine life from turning the hull into an underwater apartment complex. As shipbuilding evolved, the problem evolved with it. When iron and steel ships became common, people might have expected the problem to disappear. It did not. Steel solved many structural problems, but it created another challenge. A ship's hull still needed protection from the water, and the organisms living in the ocean still wanted to attach themselves to it. In fact, the problem became even more important as ships became larger and faster. A modern container ship may travel thousands of kilometers across the ocean. Every extra bit of resistance matters. A small increase in drag repeated over millions of meters of travel can translate into enormous fuel consumption, and fuel is one of the biggest operating costs for commercial ships. This is where anti-fouling coatings became incredibly important. The basic idea is simple: create a surface that marine organisms do not want to attach to, or, more accurately, create a surface that makes it difficult for them to survive and establish themselves. That is why many ships have a distinctive red, orange or brownish coating below the waterline. The color itself is not what makes the coating work. The important part is the chemistry inside the coating. Historically, one of the most famous solutions involved copper. Copper compounds can interfere with marine organisms and make the surface hostile to many species that would otherwise settle there. Over time, anti-fouling technology became more sophisticated. Paint manufacturers developed coatings designed to release active substances slowly into the surrounding water. The goal was not to release everything at once, it was to provide protection over long periods while the ship remained at sea. But there was a major problem: if the coating released too much harmful material, it could damage marine ecosystems, and this created an entirely new challenge for the maritime industry. How do you protect a ship from the ocean without harming the ocean? That question changed anti-fouling technology forever. One of the most famous examples was tributyltin, commonly known as TBT. For decades, TBT-based coatings were extremely effective. Marine organisms struggled to grow on treated surfaces. Ships stayed cleaner, fuel efficiency improved, maintenance became easier. It seemed like an almost perfect solution, but then scientists began noticing something deeply concerning. Even tiny amounts of TBT could have serious effects on marine organisms. The chemical could persist in the environment and affect creatures far away from the ship itself. Certain shellfish populations suffered dramatic biological effects. The technology that had been protecting ships was creating problems beneath the waves. Eventually, international regulations moved against harmful organotin anti-fouling systems. This was an important turning point. The goal was no longer simply to stop barnacles. The goal became finding smarter ways to control marine growth without creating another environmental disaster. Modern anti-fouling coatings can use different technologies depending on the vessel and its operating conditions. Some rely on carefully controlled biocides, others use advanced polymers and special surface properties. Some coatings are designed to slowly wear away as the ship moves through the water. This sounds strange. Why would anyone intentionally design paint to disappear? Because controlled erosion can actually be useful. Imagine the hull covered with a protective layer. As the ship travels through the ocean, the outer surface slowly wears away. This helps expose fresh coating while removing organisms attempting to establish themselves. Instead of allowing a thick layer of biological growth to remain permanently attached, the coating continuously renews its surface. But anti-fouling is not only about preventing barnacles. There is another reason it matters. A ship's underwater hull is engineered to move through water efficiently. Every curve, every angle and every surface is carefully designed. Naval architects spend enormous amounts of time trying to reduce resistance. Then imagine covering that carefully engineered surface with thousands of tiny organisms. It is like putting rough sandpaper across a surface designed for smooth airflow. The ship can still move, but it has to work harder. That means more engine power, more fuel, more emissions, and higher operating costs for a small recreational boat. That might mean slower performance and a bigger fuel bill for a massive commercial vessel operating almost continuously. The consequences can become enormous. And there is another fascinating problem. Ships can become biological transport systems. When organisms attach themselves to a hull, the ship can carry them from one part of the world to another. A species that naturally belongs in one ecosystem could potentially arrive in another ecosystem thousands of kilometers away. If it survives and establishes itself, it can compete with native species and disrupt local environments. So anti-fouling technology is not just about keeping ships clean, it can also help reduce the accidental transportation of marine organisms across oceans. But keeping a ship's hull protected is not as simple as painting it once and forgetting about it. Ships operate under extreme conditions. Salt water constantly attacks surfaces. Mechanical damage can occur. Propellers create powerful water movement. Ships may spend months at sea, and different parts of the hull experience different levels of stress. That is why modern marine coatings are usually part of a complete protection system. Underneath the anti-fouling layer, there may be primers and protective coatings designed to prevent corrosion, and corrosion is another enemy that ships absolutely cannot ignore. Water and steel are not good friends, especially when salt is involved. Without proper protection, corrosion can slowly weaken metal structures and create expensive maintenance problems. So that simple red area you see beneath a ship may actually be the visible part of a much more complicated engineering system. Protection against marine growth, protection against corrosion, improved hydrodynamic performance, reduced maintenance, lower fuel consumption, and potentially fewer environmental problems caused by transported organisms, all hidden beneath the waterline. And there is something ironic about the entire story. The ocean is both the reason ships exist and one of their greatest enemies. Ships were created to conquer distance across the sea, but the sea constantly tries to reclaim them. Barnacles attach themselves, algae spreads, corrosion begins, waves pound the hull, saltwater attacks the metal, and microscopic life is always searching for somewhere to settle. The anti-fouling layer is essentially the ship's invisible defense system. It stands between a carefully engineered machine and an ecosystem that wants to cover it with life. And the next time you see a giant cargo ship entering a harbor, look carefully at the part beneath the waterline. That red layer may seem like nothing more than paint, but it represents centuries of experimentation, engineering, chemistry, and hard lessons learned at sea. Without it, the ship would still float, its engines would still run, its propeller would still turn, but slowly, the ocean would begin to change the way that ship moves. More organisms would attach, the hull would become rougher, resistance would rise, fuel consumption would increase, maintenance would become more frequent, and the cost of every journey could climb. So the real story of that red layer is not about paint, it is about the constant battle between human engineering and nature, a battle that ships have been fighting for thousands of years. And every time a modern vessel crosses an ocean with a clean underwater hull, that quiet battle is happening again, thousands of kilometers from land, hidden beneath the waves where almost nobody can see it. A thin layer of specialized coating is doing its job, keeping the ocean from taking the ship back.